Well, sorry guys, my video just cut off after 30 minutes, so I have to restart my video here. I was just starting to talk about the geometric significance of a 3 by 3 matrix when you find its determinant. And what the answer to it really is that if you take a 3 by 3 matrix, of course we can take its determinant by doing the arrow method or a cofactor expansion. But it turns out that the absolute value of whatever the determinant of that matrix is measures the volume. It measures the volume of the box, or the parallelepiped is the fancy word for it. Parallelepiped, whose sides or whose edges are formed by the row vectors of A. So you see, you have 3 rows to the matrix. That's going to give you 3 vectors in 3-dimensional space. So you might have a vector here, here, and here, right? And you can then extend. These dotted lines are showing how you can extend the picture and get basically a box. It's just a slanted parallelepiped right there. So that volume is measured by this determinant. For example, if the determinant comes out to 0, this is going to have a really important meaning for us later on. If the volume is 0, if the determinant is 0, it just means that all 3 vectors that you were using to form this box, all 3 of them lay flat in the same plane. And that's something that we're going to care about when we get into chapter 4. So we can tell whether 3 vectors are coplanar, whether they are in the same plane, by throwing them into the rows of a 3 by 3 matrix and then taking the determinant to see whether it's 0 or not. Okay? So anyway, there is a second reason why the determinant is useful, is that the value, the number that you get for a 2 by 2 or a 3 by 3 matrix, it's telling you about the area or volume, respectively, that is created by the row vectors of that matrix. Okay? So I'm going to erase this now, and I'm going to give you another reason why we care about the determinant, which has to do with actually another formula for finding A inverse. Okay? So we can test whether the matrix is invertible by calculating its determinant and seeing if it's not 0. But even better than that, if the determinant is not 0 and we have an invertible matrix, we get what's called the adjoint method or adjoint formula for A inverse. And I'm going to write down the formula first, and then I will explain it. So the formula is the following. 1 divided by the determinant of A. That, of course, has to be non-zero on the bottom, right? Otherwise this doesn't make any sense. This is just a number. So to get the inverse of the matrix, I'm going to multiply this scalar by a matrix. And the matrix is written ADJ of A, and that's called the adjoint of A. Let me explain what the adjoint of a matrix is, okay, and how you find it. Turns out it's a pretty simple thing, okay. What you do is the following. Let me just explain it this way. I'm going to make a couple of quick definitions here to kind of tell you how you apply this formula. This is an alternative to the Gauss-Jordan method. So in chapter 2 we learned that we can use the Gauss-Jordan method, which is a long series of EROs, to find the inverse of a matrix. But this is now, in chapter 3, another way of finding the inverse of a matrix that doesn't have anything to do with EROs at all. Okay? You do have to be able to find the determinant of the matrix, okay, because that's a scalar that you're going to divide by out in front. And you have to find the adjoint of A, and I have to tell you what that is. So here's a definition. if every element of capital A is replaced by its corresponding cofactor. So if we replace every element of the matrix by the corresponding cofactor, I'm going to show you an example in a minute, we get what's called the matrix of cofactors. I sometimes will write that as M sub C. It's the matrix of cofactors. So basically, for example, if you have a 3 by 3 matrix A, so if A is 3 by 3, then the matrix of cofactors for A is literally just going to be the matrix where you take every single entry and you just fill in all of the cofactors from the matrix A into this matrix. Okay? I'm going to show you an example in just a second. But you do have to calculate a lot of cofactors. Remember, a cofactor is really a determinant of a sub-matrix, and then you have a possible sign change. So there's a lot of things to keep track of to build this matrix. However, from there, it's very easy to use this formula because the adjoint of A is just the transpose of this. Okay, so the adjoint of the matrix A, by definition, is simply the transpose of the matrix of cofactors. So that's kind of a nice thing that all you have to do to find A inverse is calculate the determinant, to put it on the bottom here, and then the adjoint of the matrix is just the transpose of what I have right here. Okay? So let's try it on an example. Let's go back to an example here. Let me just remind you, I'm just going to put that formula right here. The adjoint of A is the transpose of the matrix of cofactors. We obviously will need to know that. Okay? So here's an example. Let's suppose that my matrix A is the following matrix. Let's say 2, -3, 0, 2, 1, 5, and 0, -1, 2. Okay, I'm just going to do this with a 3 by 3. Of course, you could find the inverse of that using the arrow method. You could also find the inverse by using the Gauss-Jordan method. But what I'm trying to show you here is the adjoint method. Okay? And I also, by the way, I also have a video, another video about the adjoint method where I kind of explain this in a little bit more detail as well. So that's also probably worth taking a look at. So let's just start by finding the matrix of cofactors here for this matrix. Okay? So the matrix of cofactors, what we do is, for example, the 1, 1 cofactor, right? The 1, 1 cofactor. We cross off the first row of the first column and we take the determinant of the 2 by 2 submatrix that is left. And the determinant of that little 2 by 2 matrix is just 7. Okay? Then I have to move over to the 1, 2 position right here. This time I'll cross off the middle column. So I'm going to have these 4 numbers left. And the determinant there is 4 minus 0, which is 4. But be careful, we're talking about cofactors, so we have to switch the sign of any of these odd positions. So just to remind you again how that kind of looks, this is the plus-minus pattern for filling in the cofactors in the positions that you see. So the 1, 2 cofactor is really 4 minus 0, which is 4. That's the minor, but we have to put in a minus sign there. Okay? How about the 1, 3 cofactor? Cross off the first row and the third column. That leaves me with this little 2 by 2 matrix down here. And that is a -2, and we do not change the sign in that position. Okay? Next, I have to move down to the second row and kind of continue the process. In the second row, if I want to look, for example, at the 2, 1 position, I'm just going to cross off the second row in the first column and take the determinant of these 4 numbers. It gives me -6, but I have to change the sign. It becomes +6. Okay. I'm going to go a little bit faster through the rest of the matrix here. If I wanted to do the middle cofactor, I'm just going to take the determinant of the outside numbers, which is just 4, I don't have to change the sign on that one. Finally, the 2, 3 position is going to be the determinant of these 4 numbers, which is -2 minus 0. That's -2, but I leave it as 2 because of the sign change in that position. Okay. Down in the lower left, I just use the top right 2 by 2 determinant, which is -15, and I leave it as is. The lower bottom, let's see, I've got 10, but I have to change the sign of that. And the far lower right is actually going to give me 8, and I just leave that one as is as well. So there is the matrix of cofactors for A. So the next thing is the adjoint of A. The adjoint of A is just the transpose of this. Okay, so we're just going to take the first row and write it as the first column. The second row is going to become the second column, and the third row is going to become the third column. There's the adjoint of A. And so finally now, once I have the adjoint of the matrix, I can find the inverse by simply taking that adjoint and dividing it by the determinant. So I do need to find the determinant of A right now. Let me just do that really quickly. Okay. So the determinant of A, this one, we can just maybe do this with the arrow method because it's just a 3 by 3. So it's not too bad. Let me just do the arrow method. Here's the first diagonal, which is 4. And then the next diagonal is going to be -3, 5, and then remember we recopy the first 2 columns. Or you can just look at it in your head maybe. This diagonal has a 0 on it. Okay? The next diagonal over also has a 0 on it. Okay, and then we start subtracting the diagonals this way. There's also a 0 there. Okay, the next diagonal is -10. So I'm going to be subtracting -10, right? And then the last diagonal is -12. So I subtract -12. If you work all of that out, you should get 26. Okay? So the determinant of this matrix is 26. Remember, that's the volume of the parallelepiped that is formed by the 3 row vectors of this matrix if I view them in 3-dimensional space. Okay? That's an interpretation of this number that we've learned. But now we're seeing that we can also use that determinant to help us write down the inverse of the matrix. We simply take the adjoint, which is right here, and we simply divide it by 26. There is A inverse. Notice how messy the entries of A inverse really are. 7 over 26, 6 over 26, -15 over 26. If you actually tried to find the inverse of this matrix by using the Gauss-Jordan method, those messy fractions would be guaranteed to show up, right? You would have to deal with those kinds of numbers in doing that whole process that we learned in Chapter 2. The nice thing about this formula is it sort of pulls out this denominator out in front, right? The 1 over 26 gets factored out, leaving you with a matrix here, the adjoint of A, which is pretty clean, right? It just has nice whole numbers in it. And again, it's just the transpose of the matrix of cofactors, all right? So this is another method for finding the inverse of a matrix. Lastly, the very last thing, and this one I'm not going to go into here in this video, but there is something else that you should look up. I have another video, the same place where you found this video, something called Cramer's rule. And what that is it's a method if you have an invertible matrix A, and you're looking at a linear system. Okay, this is the very last thing. If your matrix A is invertible, there is actually a way to find out what X is by just using determinants only. In other words, you don't have to put this into A sharp. You don't have to actually find A inverse at all. You can just simply find the entries of X. This only works if A is a square matrix and specifically if it is invertible. But you can, in that case, actually solve for the unique solution. Remember, there will be a unique solution for X if A is invertible. Just emphasize this has to be invertible. So if you have an invertible coefficient matrix, there will guaranteed to be a unique solution for X. And Kramer's rule gives you that solution, or a way of getting that solution, without having to actually find the inverse of A or do any EROs at all. It's all determinant based. Okay? So I've got a video on my website that says Kramer's rule on it, and there's a couple of homework problems for you to practice that. I think I'm going to let you watch that, and we'll have time to talk more about that, that particular rule as well once we get back together again. I hope that the video has helped you. I hope it makes sense. Hopefully it's not too long. But I hope that you enjoyed seeing it a little bit ahead of time. That way, you know, hopefully you have enough time to kind of get on top of everything, get the homework done, practice some of the material as we head into the next week or so. Anyway, thank you very much for watching, and I'll see you guys all again very soon. Thank you.